Okay, so please open this page. We will do half wave and full wave rectifier circuits. Okay, is this topic covered in the theory class? Okay, so you have the basic idea of half wave and full wave rectifier. Okay, so we can just start. So you have the link, right? The link I am giving in chat if you want. Okay. So theory, procedure, oscilloscope tutorial. Okay. So this is basically what to say, a simulation of the oscilloscope you will find in the electronics lab. Okay. What does the oscilloscope do? Using oscilloscope, we can literally see a signal, or we can plot a particular signal in the time domain. The time domain means in the x-axis we have time. It could be in seconds, it could be in milliseconds, it could be in microseconds, depending on the oscilloscope. But in x-axis, you will always see time. And in the y-axis, you usually see voltage. Okay. So click on the simulation, okay, and click half wave rectifier. Okay. So are you seeing this page? All of you have got this page. All of you have come to this page, which you can see on your screens.
Yes, sir.
So this is basically a half wave rectifier circuit. The connection of this oscilloscope is a little bit misleading. The correct connection would be something like this. Can you see this whiteboard? Don't be misled by this oscilloscope connection. The circuit is like this. This is my AC source. It's a resistor. The oscilloscope, there is a two-channel oscilloscope. Okay. The first channel is connected directly across the AC source. Okay. This is channel 1. The second channel is connected across the load resistance. It is not connected. The second channel is connected across the load resistance. It is not connected across the diode, which it seems. Okay. So please don't be confused. Is this circuit clear? Using the more, what is the channel of oscilloscope? Using the more basic oscilloscope, which is cheaper, it is a two-channel oscilloscope. There are very expensive oscilloscopes in the market, like digital storage oscilloscope, where you can see up to 4 channels. 2-channel means that you can see 2 waveforms at the most simultaneously. Okay. For example, if I use a 2-channel oscilloscope in this experiment, I can see both the input and the output waveform together. If I want, I can see either the input or the output or both. Okay. Let me show you. Please note this circuit carefully. This is the connection of the oscilloscope. This is the correct connection of the oscilloscope. The oscilloscope is connected between the load and ground, not across the diode. If you connect it across the diode, it will show you a completely different waveform. Is it okay? So how to do the experiment? Let's read the instructions. First instruction is set the resistor RL. Okay. Set the resistor RL. Let us make it 500 ohms. Okay. Second point is click on the on button to start the experiment. What is that? Let's click on the on button. Okay. As I click the on button, I should see the grid visible on my screen. Okay. Note these two readings. This is the frequency and the amplitude of this signal. If I click, then double click on the sine wave button to generate the input waveform. Let us double click. Okay, I can see the input waveform. So this is an AC signal. AC signal, it has three different properties: amplitude, frequency, and the initial phase. Is it okay? Here it is assumed that initial phase is 0. So we are concerned about the amplitude and frequency. Now both of them we can change using these controls. We can increase the amplitude if I want between -2 volts to +2 volts. Minus means simply a phase shift. Okay, 180 degrees. Just make it 1 volt. And the frequency, see, I can increase the frequency of my light. Second, let us take a look at this. We are focusing on the first channel, so let us ignore this second channel for time being. Position Y. If I change this, I cannot do some reason. If I change this, I can change the position of the Y axis in the scope. And the second is, see, voltage per division. What does this mean? This means that, see, there are 8 big divisions. Okay, there are 8 big divisions in the y-axis, and voltages per division means what is the voltage range for one big division? Here it is 1 volt. Okay, so see, the peak here is 1 volt. So it is, I can measure it like this. The peak is here. The peak comprises of 1 full division in oscilloscope. Okay, and here I can see that 1 division indicates 1 volt. So my volt amplitude is 1 volt. If I make it 2 volts, see, now it is taking 2 big divisions. Each division is 1 volt. So my amplitude is 2 volts. Is it okay or not? Tell me. Before we proceed, it should be clear. What does this mean? Voltages per division. Is it okay? These are the basic controls of an oscilloscope which you will see in the lab. Unfortunately, since you cannot go to the lab at the moment, this is the best I can give you. Are there any doubts or any questions? If you don't have a, you can ask directly over the microphone, or if you don't have a microphone, you can type on chat. I would be very happy to answer your questions, because these are the very basic things of an electronics lab. Okay, so let us get these things clear before we move on with the experiment. Anybody having any questions regarding anything I have told you so far? Anyone having any questions? Someone is waiting in the lobby or something? No, I don't. Anyone? Okay. Okay, if this is clear, let us go to this one. Time in milliseconds per division. What does this mean? In the x-axis, you will see that there are 10 big divisions. Okay. And this means that one big division, this one, how much time it indicates. Currently, it is indicating 0.1 millisecond. So, this is the time period of my wave, starting from this point to ending from this point, ending to this point. This is one complete cycle. So, how much time one complete cycle is taking? Can anyone write in the chat? If one big division is 0.1 millisecond, so how much time is one complete cycle of this waveform is taking? Please write in the chat. Are you there? Because I can't. 1 millisecond. Okay, Ridhima is correct. 1 millisecond. Anybody else? You got the same answer? One big division is 0.1 millisecond as per this setting. And this entire waveform is taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 big divisions. So obviously the time period is 10 times 0.1 millisecond, that is 1 millisecond. Is it okay? So if time period is 1 millisecond, what will be the frequency? Yes, Vansita, very good. So if time period is 1 millisecond, what will be the frequency? Anyone? Yes, good, do right. Yes, 1 kilohertz, obviously. 1000 hertz or 1 kilohertz. If the time period is 1 millisecond, frequency will be 1000 hertz or 1 kilohertz. Okay. And see, that is exactly the frequency I am giving here, 1000 hertz. Okay. So, one of the most basic functions of oscilloscope is that I can measure the amplitude and the frequency of any waveform. Is it okay? I can also measure the phase difference between two signals, but that is a different story for another. Okay. Any questions regarding the basic oscilloscope functions? Anything you want to ask? Okay. So this blue waveform is my input. This waveform I'm getting from the source, sine wave source. Okay. So let us carry on. Click on the oscilloscope. Okay. Click on the oscilloscope button to get the rectified output. The rectified output I can see in channel 2. Oh, again, okay. Let's click here. Next step is click here. Okay. And now you can see the rectified output. This is the original output. This blue waveform, I am getting it from the sine wave source, and the orange waveform is the rectified output. Let us make this a little bit. Okay. The blue waveform is the original voltage. The orange waveform is the rectified output. It is possible to see both waveforms together by clicking this dual. Okay. See, we can see the both the waveforms together. Okay. Here we cannot see because the orange and the blue waveforms are superimposed on each other, but here you can see it. So this is a half-wave rectified signal. Is it okay? Once again, let's start. Set the resistance to 500 ohms. Okay. Then we click on, okay, set the voltage 1 volt, 100 hertz, 1000 hertz. Okay. See the input waveform. One volt, 100 hertz. Okay. Then turn on the sine wave. See the input. Okay. Next, we double click the oscilloscope and see the output. Okay. Is it okay? This is changed. Is it okay? So this is my input. This is my rectified output. Okay. And these are the both dual, which I can see both the signals at the same time. Any questions regarding this? Anything you want to ask? Anything you want to ask? What is RMS voltage? Anyone? What is RMS voltage?
Root mean square voltage.
Yes, root means the square voltage. What is the RMS? If the peak voltage is Vm, what is the RMS voltage? Yes, but see what is given here. Why do you think it is like this? What you are saying is correct. That is given in the books that V by root 2. Yes, but see what is given here. Why do you think they have given Vm by 2? Is this a mistake somewhere? Do you think there is a mistake somewhere? Or this is correct? Can you hear me now? Can you hear me, students? Yes, okay.
Yes, sir.
Okay, my question is, what is RMS voltage? Guddu Sharma has written that V RMS is V by root 2. Okay, that is the formula we see in books. Okay, so his answer is 100% correct. At the same time, V RMS is given to be Vm by 2 here. So the question is, who is correct and why? Can anyone try to attempt this question? Then what is the correct value? V RMS equal to Vm by root 2, as Guddu said, or it is Vm by 2 as it is given here? Which one is correct? Who wants to try? Anyone wants to think why which one is correct? Answer is both are correct. The answer what Guddu to give us is true for the normal sine wave. If the sine wave looks like this, what the sine wave we see usually, then the peak value is Vm, then V RMS is indeed Vm by root 2. So from his side, his answer is correct. But the sine wave we are encountering is half wave rectifier. So it looks like this. Okay. So what will the RMS of this one? How to find it out? V RMS will be square root of 1 by t, 0 to t by 2. Obviously, it is t by 2 because the waveform is existing only from 0 to t by 2. From t by 2 to t, there is no waveform. Vm square sine square omega t dt. Okay. This can be written as 1 by 2t, 0 to t by 2 Vm 2 Vm square sine square omega t dt. Okay. Now Vm square is a constant, so obviously it can be taken out of the integral. So Vm 1 by root 2t t by 2 sine square omega t dt. Okay. Now we can use the trigonometry formula. 1 minus 2 sine square theta, that is cos of 2 theta. So 1 minus cos of 2 theta, that is 2 sine square theta. So Vm 1 by 2t t by 2. Vishwadip Ghosh, he comes right at that. Okay. If you solve this, this part will come 0. Okay. So this will be Vm by 2t into t by 2. T gets cancelled. So this is Vm by square root of 4. That is Vm by 2. So for a half wave rectified out sine wave, the Vrms is indeed Vm by 2 as given in the virtual lab. But for a normal sine wave, Vrms is Vm by 2 as told by Guru. Is it okay? Any doubts?
No, sir.
Okay. Any doubts about the experiment? Any questions? Obviously, I will. Okay, this meeting will be ending in 3 minutes. So, as usual, we will continue in the same link. Okay, you can join from the same link. Okay. So please calculate the D2 factor. How to calculate it? The formulas are all given in the calculation part. So using this, please calculate the D2 factor and add it in your lab. Is it okay? The formulas are all given here. Just put the values of the formula. Vm you can take as 1. Okay. Any questions? Okay, so I am ending this lab. Please join again in the same link right now for the full wave rectifier part. Okay, thank you.